Messier 33, also known as the Pinwheel Galaxy, stands as one of the most captivating and enigmatic cosmic structures, inspiring awe among astronomers and stargazers alike. As the third largest member of the local group, after Andromeda, M31, and the Milky Way, it offers an unparalleled window into the processes shaping spiral galaxies. Nestled approximately 2.73 million light-years away, this celestial marvel is more than a collection of stars, it is a dynamic system that holds secrets of the cosmos' past, present, and future. At its core, M33 boasts a mesmerizing spiral structure, a cosmic dance of countless stars intertwined with vast swathes of interstellar gas and dust. Unlike its larger counterparts, it lacks a well-defined central bulge, a characteristic that has long puzzled researchers. This distinct morphology, often referred to as a flocculent spiral, suggests a less violent history than the grand spirals of Andromeda or the Milky Way. Scientists hypothesize that its relatively quiescent past has preserved much of its primordial structure, providing an exceptional lens through which to study galactic formation and evolution. One of its most striking features is its prolific star-forming regions. Among these, NGC 604 stands as a cosmic jewel, a sprawling nebula over 1,500 light-years in diameter, making it one of the largest H2 regions known. This stellar nursery teems with activity, where the gravitational collapse of gas clouds triggers the birth of massive, luminous stars. These newborn giants emit torrents of ultraviolet radiation, ionizing the surrounding gas and creating a brilliant display of light. NGC 604 alone has been a focus of numerous studies due to its size and complexity, making it an ideal laboratory for understanding the interplay between star formation and feedback processes. The abundance of neutral hydrogen in this galaxy further underscores its scientific significance. Radio observations have revealed an intricate network of gaseous filaments extending well beyond its visible disk, hinting at a vast, unseen reservoir of matter. This extensive hydrogen envelope fuels ongoing star formation and provides crucial insights into mass distribution. By studying the rotation curves of M33, astronomers have uncovered compelling evidence of dark matter, a mysterious, invisible substance that constitutes a significant portion of the universe's mass. Its relatively simple structure, devoid of a massive bulge, offers a clearer view of how dark matter influences the dynamics of spiral galaxies. Beyond its physical attributes, this spiral system plays a key role in the intricate gravitational ballet of the local group. Tidal interactions with Andromeda have left subtle imprints on its structure, such as warped outer regions and elongated stellar streams. These gravitational encounters may foreshadow a future merger, as simulations suggest that the two galaxies could collide long before the Milky Way becomes involved. Such events are not merely destructive but also creative, as they can trigger bursts of star formation and reshape the evolving structures. Advancements in observational technology have revolutionized the study of M33. From the Hubble Space Telescope to ground-based observatories equipped with adaptive optics, astronomers have been able to peer deeper into its heart, unraveling its stellar populations and chemical composition. Infrared observations have revealed hidden pockets of star formation and the distribution of interstellar dust. Meanwhile, X-ray studies have uncovered a population of compact objects, including neutron stars and black holes, remnants of massive stars that have reached the end of their life cycles. Its relatively close proximity makes it an ideal target for the search for exoplanets. While most planet-hunting missions focus on the Milky Way, this galaxy presents an intriguing opportunity to explore planetary systems in an entirely different environment. Detecting exoplanets here remains a challenge, given the distance, but ongoing advancements in telescope sensitivity and data analysis hold promise for future discoveries. Such findings could provide invaluable context for understanding how planetary systems form and evolve under varying cosmic conditions. In the realm of cosmology, M33 serves as a cornerstone for calibrating the cosmic distance ladder. Its Cepheid variable stars, whose brightness oscillates with a regular period, are crucial for determining precise distances to nearby galaxies. By refining these measurements, astronomers can improve estimates of the Hubble constant, the rate at which the universe expands. Discrepancies in this value derived from different methods remain one of modern astrophysics' most pressing mysteries, and this spiral system continues to play a pivotal role in the ongoing debate. This galaxy also holds a special place in the cultural and historical fabric of astronomy. Its discovery is often attributed to the Italian astronomer Giovanni Battista Hodierna in the 17th century, though it may have been observed by ancient stargazers long before telescopes existed. Charles Messier later catalogued it as M33 in 1764, solidifying its place among celestial objects of interest. Over the centuries, it has inspired countless observers, from amateur astronomers marveling at its faint glow through backyard telescopes to scientists unlocking its secrets with cutting-edge instruments. In recent years, M33 has become a focal point for citizen science initiatives, inviting enthusiasts worldwide to contribute to its study. Projects like Galaxy Zoo have enabled the public to classify its features, while online platforms allow users to analyze telescope data and identify transient phenomena, such as supernovae or variable stars. This democratization of astronomy not only accelerates scientific discovery but also fosters a deeper connection between humanity and the cosmos. As we continue to explore its mysteries, the significance of this spiral galaxy extends beyond the realm of science. It serves as a reminder of our place in the universe, a single species on a tiny planet orbiting an ordinary star, gazing at a vast, interconnected web of galaxies. Its intricate beauty and complex dynamics challenge us to expand our understanding of the cosmos and our role within it. Whether through the lens of a telescope or the pages of a research paper, this celestial marvel invites us to ponder fundamental questions. Where do we come from? What is our place in the grand structure of the universe? And what lies beyond the horizon of our current knowledge? The journey of discovery is far from over. Each new observation, each refined theory, brings us closer to unraveling the enigma of this spiral masterpiece. As technology advances and our curiosity deepens, we can only imagine what revelations await in its uncharted depths. From its radiant star-forming regions to its dark matter halo, from its gravitational interactions to its role in cosmic distance measurements, M33 stands as a testament to the enduring quest for knowledge, a pursuit that unites us across time and space. Often referred to as the star-spangled spiral, it remains an inexhaustible source of wonder. Its seemingly tranquil yet richly detailed structure is a living archive of cosmic history, each star and nebula a chapter in an ongoing story billions of years in the making. As we dive deeper into the specifics of its composition, we uncover a tapestry woven with not only the fundamental building blocks of the universe but also the potential to rewrite many long-standing theories about galactic dynamics and evolution. One of the most intriguing aspects of this system is its metal content, or rather, its relative scarcity of heavy elements compared to other spirals. Astronomers have discovered that the intergalactic Voyager, as it's sometimes called, exhibits a lower metallicity gradient than expected, meaning the proportion of elements heavier than hydrogen and helium remains relatively consistent throughout. This finding challenges conventional wisdom, which suggests that heavier elements, forged in the cores of stars and distributed by supernovae, accumulate more densely near a galaxy's center. The unusually flat metallicity gradient suggests a less turbulent history, with fewer mergers or interactions to disrupt and redistribute stellar and gaseous components. Its relatively pristine nature also makes it an ideal candidate for studying early galactic evolution. An abundance of blue, short-lived stars offers a window into the processes that dominated the universe during its more youthful epochs. These stars, often clustered in open stellar associations, provide invaluable clues about the initial conditions required for star formation. Detailed spectroscopic analyses of these regions have revealed a chemical fingerprint pointing to a system relatively unspoiled by the accretion of smaller, metal-rich galaxies, a feature that sets it apart from the more interaction-dominated histories of the Milky Way and Andromeda. Yet, even in its relative isolation, this spiral has not escaped the gravitational influences of its cosmic neighborhood. Subtle distortions in its outer regions suggest that it is engaged in a delicate gravitational dance with Andromeda. These interactions may be responsible for the faint, extended disk of stars and gas surrounding it, a feature that, while difficult to observe, carries vital information about mass distribution in the enigmatic dark matter halo. The study of these outer structures has benefited immensely from advanced techniques such as weak gravitational lensing, which allows astronomers to map the invisible scaffolding shaping its evolution. The dark matter halo, sometimes poetically referred to as the invisible cloak, is one of its most enigmatic features. By meticulously measuring the rotation curves of stars and gas clouds, researchers have concluded that the majority of its mass lies not in luminous matter but in this mysterious, unseen component. Understanding the distribution and properties of this dark matter is critical for piecing together the puzzle of how galaxies form and evolve. Moreover, M33 serves as a natural laboratory for testing alternative theories of gravity, such as modified Newtonian dynamics, MOND, which propose different explanations for the observed discrepancies in galactic rotation. While the invisible cloak exerts its influence silently, this galaxy is anything but quiet when it comes to star formation. The disk is punctuated by myriad H2 regions, where intense ultraviolet radiation from young, massive stars ionizes surrounding gas clouds. These regions are often surrounded by stellar clusters in various stages of development, offering a timeline of stellar evolution that spans millions of years. By studying these clusters, astronomers can trace the life cycle of stars and the mechanisms driving their formation. The complex interplay of gravity, radiation pressure, and magnetic fields in these regions continues to challenge our understanding of the processes shaping galaxies on both small and large scales. Among its most fascinating discoveries are its population of variable stars. Cepheid variables, in particular, have proven invaluable as cosmic distance markers due to their well-defined period-luminosity relationship. The presence of numerous Cepheids has allowed astronomers to refine measurements of its distance with unprecedented precision. Additionally, the galaxy harbors a wealth of other variable stars, including RR Lyrae stars, long-period variables, and eclipsing binaries. These stars not only provide a deeper understanding of structure but also serve as critical benchmarks for calibrating distances to more remote systems. Its relationship with Andromeda has long been a topic of intense study. The two are connected by a tenuous filament of gas, a remnant of past interactions that hints at their shared history. This filamentary bridge, barely visible even with the most sensitive instruments, is a testament to the intricate gravitational interplay shaping the local group over billions of years. Simulations of these interactions suggest that M33 and Andromeda have exchanged material on multiple occasions, enriching each other's star-forming potential while subtly altering structural dynamics. As we look ahead, its future is inextricably tied to the destiny of the local group. Over the next few billion years, it is expected to experience a series of increasingly close encounters with Andromeda, culminating in a dramatic merger. This cosmic event, though seemingly cataclysmic, will ultimately give rise to a new galaxy, blending stars, gas, and dark matter into a unified whole. Observing M33 in its current state offers a rare opportunity to study a system on the cusp of such a monumental transformation. Technological advancements promise to deepen our understanding in the coming decades. The James Webb Space Telescope, JWST, is poised to revolutionize our view, probing cooler regions in exquisite detail and revealing previously hidden aspects of the interstellar medium. Meanwhile, next-generation ground-based observatories such as the Extremely Large Telescope, ELT, will push the boundaries of resolution and sensitivity, uncovering faint stellar populations and mapping dynamics with unparalleled precision. In parallel, the search for signs of life remains an intriguing, albeit highly speculative, frontier. While the chances of detecting extraterrestrial civilizations here are exceedingly slim, its abundant star-forming regions and relatively stable environment make it an intriguing candidate for astrobiological studies. Advances in radio astronomy, such as those enabled by the Square Kilometre Array, SKA, could one day allow us to search for artificial signals emanating from distant civilizations, expanding the horizons of humanity's quest to answer the age-old question: are we alone in the universe? Ultimately, the enduring allure of this galaxy lies not only in its scientific richness but also in its ability to inspire. It stands as a beacon of the unknown, a reminder that the universe is vast, complex, and full of surprises. Whether through the lens of cutting-edge telescopes or the imaginations of those who dream of distant worlds, it continues to captivate, inviting us to explore, to learn, and to marvel at the boundless wonders of the cosmos. The galaxy known as Messier 33 continues to captivate humanity's imagination, serving as both a key scientific target and a source of cosmic wonder. Its intricate structure, evolutionary history, and dynamic interactions offer a boundless reservoir of mysteries for astronomers and theorists to unravel. Often referred to as the cosmic tapestry or stellar canvas, this spiral system demonstrates the profound diversity and complexity of galactic evolution, revealing truths that extend far beyond its 2.73 million light-year distance from Earth. Renowned for its elegantly designed flocculent spiral arms, M33's structure is less tightly wound than those of Andromeda or the Milky Way. These arms, woven with interstellar gas and dust, cradle stellar nurseries teeming with activity. Unlike galaxies with prominent bulges, such as Andromeda, its central core is modest, almost understated, consisting of older stars glowing faintly in the blue-white spectrum. This structural simplicity is deceptive, as beneath this tranquil appearance lies a hotbed of activity that holds answers to some of astrophysics' most enduring questions. One of the standout features of this system is its extraordinary rate of star formation, occurring at levels disproportionate to its relatively modest mass. The so-called stellar forge of M33 has puzzled scientists for decades. Why does it form stars so efficiently compared to others of similar size? Studies have pinpointed its abundant reservoirs of cool molecular hydrogen as a key driver. Observations with radio telescopes, such as the Very Large Array, VLA, have revealed vast regions rich in this star-forming fuel. Unlike the Milky Way, where such gas is confined to the inner disk, the stellar canvas extends its molecular material far into the outer arms, suggesting a dynamically stable environment capable of sustaining star formation over billions of years. Among its stellar factories, the region known as NGC 604 takes center stage. Spanning over 1,500 light-years, this immense H2 region is a breeding ground for massive stars, rivaling even the largest stellar nurseries in the Milky Way, such as the Tarantula Nebula. These newborn giants, often more than 50 times the mass of the Sun, burn through nuclear fuel at astonishing rates, emitting ultraviolet radiation that ionizes surrounding hydrogen gas. This process creates a glowing nebula whose intricacy has been likened to cosmic lacework. What makes NGC 604 particularly significant is its resemblance to star-forming regions found in the early universe. Studying this nebula allows astronomers to better understand how galaxies like M33 might have appeared in their infancy. The system's vast population of young stars is accompanied by an impressive collection of older stars, primarily residing in the central region and inner arms. These include red giants and ancient globular clusters, providing a fossil record of the galaxy's earliest epochs. Through their chemical compositions, astronomers can piece together a timeline of formation and enrichment processes. For instance, the low metallicity of older stars suggests an origin in a relatively isolated environment, free from significant mergers or accretion events that might have disrupted early development. Its relationship with Andromeda is a story of gravitational intrigue. Observations suggest that the two galaxies have been exchanging material for billions of years, a cosmic dialogue marked by subtle tidal distortions and shared gas streams. The discovery of a faint hydrogen bridge connecting them has fueled speculation about their intertwined history. Computer simulations suggest that a close encounter several billion years ago likely influenced the spiral structure and contributed to its robust star formation. These interactions are not merely relics of the past but continue to shape the dynamics of the local group today. While much of the focus has centered on the luminous disk, its dark matter halo remains one of its most perplexing attributes. Like most galaxies, the majority of its mass resides in an invisible component, inferred through gravitational effects. Unlike the Milky Way, which boasts a more complex dark matter halo due to a rich merger history, M33 offers a cleaner system for studying this elusive substance. Detailed measurements of its rotation curve have revealed an unexpectedly smooth distribution of dark matter, challenging theoretical models and suggesting that its properties may vary across different galaxies. Another fascinating feature is its collection of X-ray sources, including neutron stars, black holes, and supernova remnants. These objects, remnants of massive stars that have reached the end of their life cycles, are scattered throughout the system, often clustered in regions of active star formation. By analyzing their X-ray emissions, astronomers can probe extreme physics governing these dense objects, from the nature of accretion disks to the behavior of matter under intense gravitational forces. The discovery of ultraluminous X-ray sources, ULXs, has further intrigued researchers, as these enigmatic objects may represent intermediate-mass black holes, an elusive category bridging the gap between stellar mass and supermassive black holes. M33's proximity also makes it an invaluable testing ground for detecting exoplanets in other galaxies. While the vast distances involved make such detections extraordinarily challenging, advancements in microlensing and transit photometry have opened new possibilities. Detecting planets here would mark a groundbreaking milestone, offering insights into planetary formation and evolution under conditions different from those in the Milky Way. Such discoveries could even refine the search for habitable zones in galaxies beyond our own, expanding the scope of astrobiology into an entirely new domain. This system also plays a crucial role in understanding cosmic expansion. Its Cepheid variable stars and eclipsing binaries serve as critical benchmarks for calibrating the cosmic distance ladder, allowing astronomers to refine measurements of the Hubble constant. This value, which describes the rate at which the universe is expanding, remains a source of significant tension in cosmology, with different measurement methods yielding conflicting results. By improving distance estimates, astronomers hope to resolve these discrepancies and shed light on the underlying physics driving cosmic expansion. As we continue to explore its mysteries, M33's significance extends beyond the realm of science. It serves as a reminder of our place in the universe, a single species on a tiny planet orbiting an ordinary star, gazing at a vast, interconnected web of galaxies. Its intricate beauty and complex dynamics challenge us to expand our understanding of the cosmos and our role within it. Whether through the lens of a telescope or the pages of a research paper, this celestial marvel invites us to ponder fundamental questions. Where do we come from? What is our place in the grand structure of the universe? And what lies beyond the horizon of our current knowledge? The journey of discovery is far from over. Each new observation, each refined theory, brings us closer to unraveling its enigma. As technology advances and curiosity deepens, we can only imagine what revelations await in its uncharted depths. From its radiant star-forming regions to its dark matter halo, from gravitational interactions to its role in cosmic distance measurements, M33 stands as a testament to the enduring quest for knowledge, a pursuit that unites us across time and space. Technological advancements promise to deepen our understanding in the coming decades. The James Webb Space Telescope, JWST, is poised to revolutionize our view, probing cooler regions in exquisite detail and revealing previously hidden aspects of the interstellar medium. Meanwhile, next-generation ground-based observatories such as the Extremely Large Telescope, ELT, will push the boundaries of resolution and sensitivity, uncovering faint stellar populations and mapping dynamics with unparalleled precision. In parallel, the search for signs of life remains an intriguing, albeit highly speculative, frontier. While the chances of detecting extraterrestrial civilizations here are exceedingly slim, its abundant star-forming regions and relatively stable environment make it an intriguing candidate for astrobiological studies. Advances in radio astronomy, such as those enabled by the Square Kilometre Array, SKA, could one day allow us to search for artificial signals emanating from distant civilizations, expanding the horizons of humanity's quest to answer the age-old question: are we alone in the universe? Ultimately, the enduring allure of this galaxy lies not only in its scientific richness but also in its ability to inspire. It stands as a beacon of the unknown, a reminder that the universe is vast, complex, and full of surprises. Whether through the lens of cutting-edge telescopes or the imaginations of those who dream of distant worlds, M33 continues to captivate, inviting us to explore, to learn, and to marvel at the boundless wonders of the cosmos. Future missions and observatories promise to unlock even more of M33's secrets. The James Webb Space Telescope, with its unparalleled sensitivity in the infrared spectrum, will allow astronomers to peer through its dust clouds, revealing hidden stellar nurseries and the earliest stages of star formation. Meanwhile, next-generation radio telescopes like the Square Kilometre Array will map gas dynamics in unprecedented detail, offering new insights into the processes governing its evolution. These advancements will not only enhance our understanding of this spiral system but also provide a framework for studying galaxies across the cosmos. Ultimately, The allure of M33 lies not just in its scientific richness but in its ability to evoke a profound sense of wonder. As humanity continues to explore its mysteries, it serves as a reminder of the vastness and complexity of the universe. Its glowing arms, stellar nurseries, and enigmatic dark matter halo are more than just objects of study, they symbolize the unending quest for knowledge, inspiring us to look beyond our own galaxy and dream of what lies beyond. Often referred to as the stellar crucible, this system continues to surprise and inspire with its intricate dynamics, unique star-forming activity, and profound role in unlocking universal mysteries. One of its most fascinating aspects is the interplay between ancient cosmic history and ongoing evolution, creating a living portrait of the universe in transition. At the heart of its intrigue lies dynamic spiral arms adorned with an unparalleled abundance of massive star-forming regions. Unlike the tightly wound arms of the Milky Way, they appear diffuse yet richly detailed, hosting an almost theatrical display of cosmic creation. Its most famous H2 region, NGC 604, exemplifies this. Containing over 200 massive stars that are less than 5 million years old, this nebula emits an astonishing amount of ultraviolet radiation, lighting up surrounding clouds of gas in a dazzling display. Studying NGC 604 has allowed astronomers to trace the feedback mechanisms between young, hot stars and their environments. This interaction profoundly shapes not only local nebulae but the broader evolution of the galaxy itself. What sets M33 apart from its counterparts is the sheer efficiency and consistency of its star formation. While most galaxies exhibit declining star formation as they age, this one has defied expectations, continuing to convert gas into stars at rates rivaling much larger galaxies. Observations suggest that its interstellar medium is unusually stable, with turbulence levels low enough to allow gravity to dominate and trigger frequent collapses of gas clouds into new stars. This efficiency makes it an unparalleled model for understanding how gas-rich galaxies may have behaved during the universe's younger, more active phases. Adding to its fascination is a rich population of variable stars. These, particularly Cepheid variables and RR Lyrae stars, act as celestial lighthouses, their rhythmic pulsations providing astronomers with a means to measure distances across vast cosmic scales. Cepheids in M33 are among the most precisely studied in the local group, offering insights into both its internal structure and the broader scale of the universe. Their periodic luminosity variations have allowed scientists to refine distance measurements not only to this galaxy but to those far beyond, contributing directly to efforts to resolve the Hubble constant tension, one of modern cosmology's most debated puzzles. Beyond its stars, M33 is also a showcase of exotic celestial phenomena. Among its treasures are ultraluminous X-ray sources, ULXs, mysterious objects whose brightness exceeds what is typically expected from individual stellar remnants like neutron stars or black holes. Some ULXs are suspected to be intermediate-mass black holes, rare objects whose existence could bridge the gap between stellar mass and supermassive black holes. The mechanisms powering these ULXs remain a topic of intense research, as they might involve unusual accretion processes or even entirely new physics. A particularly tantalizing mystery is its vast, enigmatic dark matter halo. While dark matter is an essential component of all galaxies, shaping their structures and influencing their evolution, this system presents an unusually clean model for studying this phenomenon. Its lack of a significant central bulge allows for analysis with minimal interference from other structural complexities. Observations of its rotation curve, how stars and gas move at different distances from the center, have revealed the unmistakable signature of dark matter. However, the smoothness of the curve has challenged traditional models, hinting at the possibility of unknown properties or distributions of dark matter that may vary from galaxy to galaxy. This has placed M33 at the forefront of efforts to unravel one of the universe's most profound enigmas. Its gravitational relationship with Andromeda adds another layer of intrigue. Recent simulations suggest that this system is not merely a passive satellite of its larger neighbor but an active participant in a gravitational tango. Evidence of past tidal interactions, such as distorted outer structures and elongated streams of gas, point to a complex history of close encounters. These interactions may have influenced its spiral structure and even fueled ongoing star formation. The two galaxies are expected to continue their gravitational dance over the next several billion years, with M33 likely to merge with Andromeda long before the latter collides with the Milky Way. This cosmic collision, while destructive on the surface, will ultimately birth a new galaxy, blending the stars and dark matter of both systems into a single, larger entity. In addition to its physical and dynamic properties, M33 has become a key player in the search for exoplanets beyond the Milky Way. While most discoveries have been confined to our galaxy, the possibility of detecting planets in this distant spiral has intrigued astronomers. Techniques such as microlensing, which relies on the gravitational bending of light by massive objects, have opened the door to identifying planets in other galaxies. Although no exoplanets have yet been confirmed, its abundant star-forming regions and relatively stable environment make it a promising candidate for future detections. Often considered a hidden gem of the local group, this stellar system reveals an almost poetic balance between structural elegance and scientific complexity. Its loosely bound spiral arms, dotted with stellar nurseries, act as celestial canvases where the drama of star formation unfolds. Unlike its larger siblings, Andromeda and the Milky Way, this cosmic neighbor has experienced a less chaotic evolutionary history, making it a pristine example of galactic dynamics untouched by excessive interactions or violent mergers. One of its standout features is an extraordinary star-forming efficiency. Scientists have observed that it forms stars at an almost unmatched rate for its size. This has led researchers to dub it a stellar factory, where molecular gas is consistently transformed into new generations of stars. The ability to sustain such activity over billions of years can be attributed to extensive reservoirs of cold hydrogen gas, which fuel the ongoing birth of massive, short-lived stars that illuminate the spiral arms like cosmic beacons. Among these arms lies one of the most iconic regions, the massive H2 region known as NGC 604. This colossal stellar nursery, visible even from Earth with modest telescopes, is home to over 200 massive stars whose intense ultraviolet radiation ionizes the surrounding gas. This process results in an ethereal, glowing nebula that stretches over 1,500 light-years. NGC 604 dwarfs many similar regions, such as the Orion Nebula in the Milky Way. Astronomers often refer to it as a miniature version of the conditions that existed in the early universe, providing a glimpse into how the first galaxies may have formed. The vast wealth of variable stars also makes this system an astronomical treasure, acting as timekeepers and distance markers across the cosmos. Cepheid variables have been crucial in refining the cosmic distance ladder, providing astronomers with precise measurements not only to this galactic neighbor but also to systems far beyond. Its well-studied variable stars have played a key role in calibrating the Hubble constant, a measure of the universe's expansion rate, offering valuable insights into one of modern cosmology's greatest mysteries. Beyond its well-lit spiral arms, the luminous structure hides a darker, more enigmatic feature, a vast dark matter halo. This invisible component, which dominates the galaxy's mass, has been studied through its gravitational effects on the rotation of stars and gas. Unlike many others, this gravitational enigma displays an unusually smooth rotation curve, suggesting that dark matter is distributed in a way that challenges current theoretical models. This makes it a prime candidate for testing alternative gravity theories and exploring the elusive nature of dark matter, a substance that holds the key to understanding the universe's structure. It is also a hotbed of high-energy astrophysics. Ultra-compact X-ray sources, ULXs, scattered across its disk have intrigued astronomers, as their brightness defies conventional explanations. These luminous sources may represent intermediate-mass black holes, which are rare and poorly understood. By studying these objects, scientists hope to bridge the gap between stellar mass and supermassive black holes, shedding light on how such enigmatic objects form and grow over cosmic timescales. Gravitational interactions with Andromeda have left subtle yet discernible marks on its structure. These include warped outer regions and streams of gas connecting the two galaxies, remnants of past encounters that suggest an intricate history of tidal interactions. Such gravitational exchanges have shaped its current state and forecast its future. In billions of years, it is expected to merge with Andromeda, a collision that will forever alter the dynamics of the local group and reshape both galaxies into a single, massive elliptical structure. This dynamic system has also been considered a frontier for exoplanet searches beyond the Milky Way. Though detecting planets in such a distant system is extraordinarily challenging, the prospect is not beyond reach. Gravitational microlensing offers a promising method, and the abundance of young, luminous stars provides an ideal backdrop for such studies. Finding exoplanets here would expand our understanding of planetary systems and their formation under diverse cosmic conditions, hinting at the potential for life in environments vastly different from our own. What makes this spiral system even more compelling is its role as a laboratory for studying the universe's evolution. Its relatively simple structure, free from the complexities of a massive central bulge, allows astronomers to test theories about the formation and development of galaxies in isolation. This, combined with its proximity, has turned it into a cornerstone for modern astrophysics. Its interactions, star-forming processes, and variable stars are essential tools for unraveling mysteries that stretch across time and space. As technology advances, the shimmering forge of cosmic creation promises to reveal even more secrets. Observatories like the James Webb Space Telescope and the Extremely Large Telescope are poised to dive deeper into its star-forming regions, unveiling hidden populations of stars and mapping the intricate dance of gas and dust that drives its evolution. It will also benefit from upcoming radio and X-ray observatories, which will explore its dark matter halo and high-energy phenomena with unprecedented precision. Ultimately, this celestial enigma stands as a testament to the universe's boundless complexity and beauty. From its luminous spiral arms to its invisible dark matter halo, the galactic canvas invites us to explore, question, and dream. It serves as a reminder of how much remains to be discovered, not only within its boundaries but across the cosmos. As our gaze extends further into the stars, this spiral marvel remains a guiding light, inspiring humanity to reach for the unknown and uncover the secrets of existence itself. Nestled just over 2.7 million light-years away, this wanderer continues to challenge and inspire as one of the local group's most dynamic and mysterious members. Its unassuming size compared to Andromeda or the Milky Way hides a realm of intricate astrophysical phenomena that ignite the imagination. This galactic neighbor, with its breathtaking flocculent spiral arms and unique evolutionary story, holds the key to unraveling some of the universe's most profound mysteries, ones that stretch beyond the limits of human understanding. One of the most extraordinary aspects of the celestial architect is its enigmatic relationship with Andromeda, the dominant force in the local group. Observations have revealed faint tidal streams of gas and stars stretching between the two galaxies, evidence of gravitational interactions spanning billions of years. The slow, cosmic ballet between these celestial giants is a dance of disruption and creation, profoundly shaping the intergalactic sculpture's structure and future. Computer simulations suggest that the stellar drifter has orbited Andromeda for eons, its gravitational pull subtly altering its trajectory and sculpting its spiral arms. These interactions may even have triggered bursts of star formation, giving rise to the luminous regions scattered across its disk. Yet, the future of the Galactic Weaver is just as fascinating as its past. Within the next several billion years, its gravitational bond with Andromeda will tighten, pulling the two galaxies closer together. Astronomers predict that this will culminate in a dramatic merger long before Andromeda collides with the Milky Way. This apocalyptic event, while seemingly destructive, will forge a new galaxy, blending their stars, gas, and dark matter halos into a harmonious whole. The beauty of such cosmic transformations lies in their duality. The destruction of old structures leads to the birth of new ones, reminder of the universe's cyclical nature. The radiant spiral, however, is more than a future participant in a galactic collision, it is a living cosmic laboratory, where the laws of physics and the forces shaping the universe can be observed in action. Its unusually abundant reservoirs of neutral hydrogen gas, extending far beyond its visible disk, fuel its prolific star-forming activity. This extended gaseous halo serves as the raw material for creating stars and offers vital clues about how the stellar choreographer interacts with its environment. Astronomers believe these reservoirs may represent remnants of ancient cosmic filaments, vast streams of matter that once served as the scaffolding for early galaxy formation. Among the cosmic artisan's greatest mysteries is its role as a beacon for studying dark matter, the elusive substance that dominates galactic mass yet remains undetectable through traditional means. The rotation curve of the galactic sculptor, meticulously measured through radio and optical observations, tells a story of an invisible mass enveloping the galaxy. Unlike systems with prominent bulges or recent merger histories, the celestial enigma offers a relatively undisturbed platform for studying the distribution of dark matter. Its smooth, steady rotation challenges conventional models of dark matter halos, hinting at new physics that could one day rewrite our understanding of the cosmos. But the mysteries of the luminous nomad extend beyond its dark matter halo and into its starry heart. Its extraordinary collection of star clusters, variable stars, and supernova remnants provides a timeline of cosmic events spanning billions of years. Each of its globular clusters serves as a time capsule, preserving the chemical and dynamical history of the galaxy's formation. Meanwhile, its population of Cepheid variables plays a critical role in refining the cosmic distance scale. These pulsating stars, with their predictable brightness variations, allow astronomers to measure distances with stunning precision, making the starry architect a cornerstone in solving the Hubble constant debate. Beyond its role in cosmic measurements, the stellar forge is a hotbed of high-energy phenomena. The presence of ultraluminous X-ray sources scattered throughout its disk raises tantalizing questions about the nature of black holes and their formation. These ULXs are brighter than expected for typical stellar mass black holes, suggesting they may host intermediate mass black holes, elusive objects that bridge the gap between stellar mass and supermassive black holes. Alternatively, some ULXs may represent exotic binary systems where compact objects accrete matter at extraordinary rates, defying the limits of conventional physics. In recent years, the nebular Voyager has become a focal point for cutting-edge technology in astronomy. The James Webb Space Telescope promises to unveil new layers of its story, peering through interstellar dust to uncover hidden stellar nurseries and faint populations of stars. Meanwhile, next-generation radio observatories like the Square Kilometre Array will map its gas dynamics in exquisite detail, revealing the gravitational influences shaping its structure and the intricate processes fueling its star formation. Even more futuristic missions aim to push the boundaries of what we can learn from the celestial wanderer. Efforts to detect exoplanets in other galaxies may one day include this spiral marvel. With advanced microlensing techniques, astronomers hope to identify planetary systems orbiting stars within its spiral arms, offering a tantalizing glimpse into the possibility of life in entirely different galactic environments. While such detections remain speculative for now, the idea of finding Earth-like worlds orbiting distant suns in the stellar tapestry is a thrilling frontier for the future of astrobiology. The northern pinwheel, as it is sometimes romantically called, also serves as a gateway to understanding galaxy evolution within the local group. Its interactions with Andromeda, its seemingly unquenchable star formation, and its pristine structure make it a bridge between isolated dwarf galaxies and massive spirals like the Milky Way. By studying its unique characteristics, astronomers hope to answer questions about the life cycles of galaxies, from their formation in the early universe to their eventual mergers and transformations billions of years later. Ultimately, this cosmic wonder is a living storybook of galactic evolution. It invites us to ponder questions that transcend science and enter the realm of philosophy. What role does it play in the grander tapestry of the universe? How does its quiet beauty, shimmering in the vastness of space, reflect the intricacy and fragility of existence itself? As we continue to explore its mysteries with ever-advancing technology, the Cosmic Maestro reminds us of the boundless depths of the cosmos, a universe full of wonders waiting to be discovered, each more surprising and inspiring than the last. The Cosmic Voyager, as this spiral galaxy is sometimes affectionately called, continues to expand the horizons of our understanding of the universe. Its role as both a scientific marvel and a philosophical beacon is unmatched, offering insights into the nature of galaxies and the forces that govern them. At every scale, from its vast dark matter halo to the smallest flickers of newborn stars, the stellar symphony provides a stage where the cosmic ballet of creation, destruction, and renewal plays out in awe-inspiring detail. One of the most fascinating ongoing areas of study in the spiral jewel involves its intricate interstellar medium. The gas and dust within this system are not just the building blocks of stars, they also serve as a record of interactions and internal processes. Recent observations using advanced radio telescopes have mapped the distribution of atomic and molecular hydrogen with incredible precision. These studies reveal a complex network of filaments, voids, and dense clouds stretching across its disk, tracing the influence of gravity, turbulence, and magnetic fields. The presence of these structures raises intriguing questions. How do such patterns emerge? What role do they play in the formation of stars? Could similar structures exist in more distant and less accessible galaxies? The nebular enigma also stands as a testing ground for one of the most profound mysteries in modern astrophysics, the nature of dark matter. while its rotation curve, showing how the speed of stars and gas changes with distance from the center, matches the predictions of dark matter models, certain subtleties challenge our understanding. For instance, its halo appears to extend far beyond its visible disk, with a smoother distribution than expected for a galaxy of its size. Some researchers speculate that this discrepancy might hint at new physics, perhaps involving self-interacting dark matter or other exotic particles yet to be discovered. The luminous sentinel also reveals its secrets through the extraordinary light of its variable stars, a celestial clockwork that has helped refine the scale of the universe. Beyond the Cepheid variables central to distance measurements, other types, such as RR Lyrae stars, long-period variables, and eclipsing binaries, offer complementary insights into its structure and history. RR Lyrae stars, for example, are particularly useful for studying the oldest stellar populations of the spiral nomad, providing a direct link to its earliest epochs. This starry wonderland also contains clues about the explosive ends of massive stars. Supernova remnants scattered throughout the galactic tapestry serve as markers of past cataclysms, where dying stars expelled their enriched material into the interstellar medium. These events play a crucial role in shaping its chemical evolution, seeding it with heavy elements that later become the building blocks of planets and, potentially, life. Some remnants have been found to harbor neutron stars or pulsars, exotic objects that offer a glimpse into the most extreme states of matter. Yet, the intergalactic muse is far from a galaxy frozen in time. Observations of its kinematics reveal ongoing accretion, where streams of gas fall into its structure from the surrounding cosmic web. These inflows provide fresh material for star formation, replenishing its reserves and sustaining its activity over billions of years. Such inflows are a critical part of a galaxy's life cycle, and the stellar enchanter offers a rare opportunity to study them in detail, thanks to its proximity and relative isolation. Another exciting frontier in the study of the starry Voyager involves its massive star clusters, particularly open clusters scattered across its spiral arms. These clusters represent different stages of stellar evolution, from blazing hot blue giants in newly formed regions to cooler, older stars in more mature groups. By analyzing these clusters, astronomers can reconstruct its star formation history, revealing bursts of activity that may have been triggered by interactions with Andromeda or other nearby systems. The gravitational relationship between the cosmic artisan and Andromeda remains a subject of deep fascination. Some researchers believe that the galactic sculptor may have originally been a satellite of Andromeda, ejected during a past close encounter. This scenario could explain some of its unique features, such as its flocculent spiral arms and extended gas envelope. If true, this history would make the northern spiral a cosmic wanderer, a system that has not only survived but thrived after being cast out from its original environment. As we peer further into the depths of the stellar nomad, the search for exoplanets within its borders grows increasingly compelling. While detecting planets in another galaxy remains an extraordinary challenge, breakthroughs in microlensing and advanced telescopes offer tantalizing possibilities. Could the spiral wanderer harbor worlds unlike anything we have imagined, orbiting stars in its spiral arms or ancient clusters? The thought of alien skies under a faraway sun, framed by the glowing light of its nebulas, fuels the imagination and pushes the boundaries of human exploration. The cosmic tapestry is more than a scientific treasure, it is a living reminder of the universe's infinite potential. Its glowing arms, dark matter halo, and vibrant star-forming regions speak to a cosmos that is dynamic, interconnected, and filled with beauty beyond comprehension. Each discovery made within the spiral luminary not only deepens our understanding of this galactic wonder but also connects us to the larger story of the universe, a story in which our own Milky Way plays a small but vital role. As humanity continues to push the frontiers of exploration, the marvelous spiral remains a guiding light, an enduring symbol of what lies beyond. It whispers of mysteries yet unsolved, of worlds yet unseen, and of knowledge yet uncovered. The journey of discovery through its starry expanse is far from over, and each new chapter reveals that the stellar beacon has much more to teach us about the cosmos, our place within it, and the boundless possibilities of the unknown. The celestial wonder, as this spiral galaxy is affectionately known, continues to reveal new layers of complexity with every technological advancement. This majestic structure serves as a microcosm of the universe's diversity, encapsulating phenomena that range from the fiery birth of stars to the quiet, unyielding influence of dark matter. It is a masterpiece of cosmic evolution, constantly evolving and interacting with its environment, and its mysteries are as profound as the vastness of the cosmos itself. One of the most captivating aspects of the spiral luminary is its role as a galactic time capsule. Its stellar populations span billions of years, from ancient stars in its halo to newly ignited giants in its star-forming regions. This broad timeline allows astronomers to reconstruct its history in unprecedented detail. By studying the metallicity of its stars, how enriched they are in elements heavier than helium, scientists have uncovered a story of gradual enrichment, punctuated by bursts of star formation likely triggered by tidal interactions with Andromeda or even smaller satellite galaxies. The cosmic artisan is also a playground for high-energy astrophysics, hosting phenomena that push the boundaries of our understanding. Among its most intriguing residents are ultraluminous X-ray sources, ULXs, which emit energy far exceeding that of typical stellar remnants. The nature of these objects remains an open question. Some astronomers theorize they may be intermediate-mass black holes, while others propose they are stellar-mass black holes in binary systems, accreting matter at extraordinary rates. The study of these enigmatic sources in the galactic jewel could lead to breakthroughs in understanding the extremes of gravity and energy. Another remarkable feature of the stellar enigma is its dynamic interstellar medium, a complex web of gas and dust that serves as both the raw material for star formation and a repository of cosmic history. Advanced radio observations have revealed that its neutral hydrogen disk extends far beyond the visible boundaries, forming a diffuse halo that interacts with the cosmic environment. This vast reservoir of gas is not static, it flows, collides, and cools, forming the seeds of future stars. The interplay of these processes within the luminous Voyager offers a glimpse into the mechanisms that sustain galaxies over cosmic timescales. The nebular symphony is also a vital piece of the local group's puzzle, with its gravitational interactions with Andromeda shaping the dynamics of the entire galactic neighborhood. Recent simulations suggest that the spiral prodigy may eventually spiral inward toward its massive neighbor, merging in a spectacular cosmic collision. This event, occurring billions of years before Andromeda and the Milky Way collide, would reshape the local group, creating a massive elliptical galaxy that blends the stars, gas, and dark matter of both systems. Observing the star-spangled spiral in its current state allows astronomers to study a galaxy on the verge of such a monumental transformation. The intergalactic beacon is also an invaluable tool for refining our understanding of the universe. Its Cepheid variable stars have provided some of the most precise measurements of the cosmic distance scale, improving estimates of the Hubble constant and shedding light on the rate of universal expansion. The role of the cosmic architect in this endeavor cannot be overstated. it serves as a bridge between nearby galaxies and the vast, uncharted territories of the cosmos. Beyond its scientific significance, the galactic nomad is a source of boundless inspiration. Its glowing arms, dotted with nebulae and star clusters, evoke a sense of wonder that transcends science. The ability to peer into this distant world, study its stars, and uncover its secrets is a testament to human curiosity and ingenuity. Looking to the future, the spiral sculptor is poised to remain a cornerstone of astronomical research. Next-generation observatories such as the James Webb Space Telescope, the Vera C. Rubin Observatory, and the Square Kilometre Array will unveil even more details about this extraordinary system. These tools will allow astronomers to map its star-forming regions, measure dark matter distribution with greater precision, and perhaps even detect faint whispers of planets orbiting stars in its spiral arms. The potential for discovery within the stellar weaver is limitless. Could its star-forming regions harbor the conditions necessary for life? Could its unique dynamics reveal new physics that challenge our understanding of gravity or dark matter? The answers to these questions lie within its luminous arms, waiting to be uncovered by future generations of explorers. Ultimately, the celestial tapestry serves as a reminder of the universe's boundless complexity and beauty. It is a place where past, present, and future of cosmic evolution converge, offering a glimpse into the forces shaping not only galaxies but the universe itself. As we continue studying this celestial masterpiece, the spiral wonder inspires us to reach further, dream bigger, and embrace the infinite possibilities of the cosmos. Its mysteries call out across the void, inviting us to discover not only the secrets of the stars but also the profound truths about our own place in the grand design of existence. The galactic masterpiece, often regarded as the quiet genius of the local group, embodies the essence of cosmic diversity, revealing an ever-expanding tapestry of phenomena that stretch the limits of scientific understanding. Though seemingly modest in size compared to its neighbors, it holds within it an intricate ecosystem of stars, gas, dust, and dark matter, each interacting in a dance of creation and destruction that has persisted for billions of years. As our technological capabilities grow, so too does our appreciation of the spiral enchanter, whose beauty and complexity continue to surprise even the most seasoned astronomers. One of the most fascinating elements of the cosmic forge is its role as a galactic living fossil. Unlike the Milky Way or Andromeda, the galactic luminary appears to have led a relatively tranquil life, free from the violent mergers that often disrupt and reshape other galaxies. This relative isolation has allowed it to maintain a purity of structure, making it an ideal laboratory for studying the processes of galactic evolution. Its spiral arms, while flocculent and less tightly wound, are remarkably intact, preserving the story of billions of years of star formation and chemical enrichment. The stellar crucible is particularly noted for its stellar nurseries, regions where new stars emerge from collapsing clouds of gas and dust. These nurseries, such as the colossal NGC 604, serve as miniature universes, each with its own unique conditions and challenges. NGC 604, with its population of massive, young stars, provides a spectacular example of how feedback mechanisms shape the interstellar medium. The intense radiation and stellar winds from these stars carve out vast cavities in the surrounding gas, creating a dynamic interplay of compression and dispersal that drives the ongoing cycle of star formation. This feedback is not just a local phenomenon, it has far-reaching implications for the evolution of the nebular artisan, influencing the distribution of gas and the eventual fate of its spiral arms. The galactic jewel is also remarkable for its chemical composition, which provides crucial insights into its history and environment. Observations reveal that the stellar symphony has a surprisingly flat metallicity gradient, meaning the proportion of heavy elements remains relatively consistent across its disk. This is unusual for a spiral galaxy, where metallicity typically decreases with distance from the center. Scientists believe this could be a result of efficient mixing processes within the spiral artisan, perhaps driven by gravitational interactions with Andromeda. Alternatively, it might reflect a unique star formation history that has avoided disruptive mergers, which often introduce sharp metallicity gradients. The celestial puzzle is home to a population of ancient globular clusters, time capsules from the earliest epochs of the universe. These tightly bound stellar collections provide a wealth of information about the conditions under which the spiral prodigy formed. By analyzing chemical signatures and stellar motions within these clusters, astronomers can reconstruct its early history, tracing its origins to a time when the universe was young and the first structures were beginning to take shape. The starry nomad's interactions with cosmic neighbors have left indelible marks on its structure and dynamics. Faint tidal streams of gas and stars connecting it to Andromeda are a testament to the gravitational forces binding the local group. Though difficult to observe, these streams carry invaluable information about past encounters and material exchanges between galaxies. Some studies suggest that the cosmic tapestry may have lost some of its outer material during close encounters, which could help explain the extended gas halo observed around both systems. Dark matter, the unseen scaffolding of the universe, plays a central role in shaping the gravitational enigma. Its rotation curve, which remains flat even at great distances from the galactic center, provides strong evidence for the existence of a massive dark matter halo enveloping the galaxy. Yet, the distribution and properties of this halo are anything but straightforward. Detailed studies of the spiral Voyager have revealed discrepancies between observations and theoretical models, suggesting that the nature of dark matter may be more complex than previously thought. These findings make it a critical testing ground for new theories of dark matter and alternative models of gravity. The intergalactic wanderer plays a pivotal role in the broader narrative of the local group. As one of its three dominant members, alongside Andromeda and the Milky Way, the spiral companion bridges the gap between smaller dwarf galaxies and the massive spirals that shape the group's evolution. Its past and future interactions influence everything from the distribution of gas to the fate of cosmic mergers. The eventual collision between the cosmic sculptor and Andromeda will redefine the structure of the local group, setting the stage for its ultimate transformation. The northern pinwheel also holds promise as a frontier for the search for extraterrestrial life. While most studies of habitable environments focus on the Milky Way, the luminous Whisper provides an opportunity to explore planetary systems in an entirely different galactic context. Its star-forming regions and relatively stable environment make it a prime candidate for astrobiological studies. Detecting exoplanets in the star-spangled spiral would be a groundbreaking achievement, expanding our search for life to an entirely new scale and offering insight into the conditions under which planets and life might arise. The future of the stellar muse is as bright as its glowing spiral arms. Upcoming missions and telescopes will continue to probe its mysteries, from mapping its dark matter halo to understanding the processes driving its extraordinary star formation. The James Webb Space Telescope, with its unmatched infrared sensitivity, will reveal hidden stellar nurseries, while the extremely large telescope will push the limits of resolution, allowing astronomers to examine individual stars and clusters in unprecedented detail. Ultimately, the celestial enigma serves as a reminder of the universe's boundless complexity. The intricate interplay of forces within it reflects the vast, interconnected web of cosmic evolution, an ongoing story that we are only beginning to understand. As we continue exploring, the spiral wonder urges us to dream beyond the limits of our own galaxy, embracing the infinite possibilities of the cosmos. In the quiet brilliance of its spiral arms, the galactic masterpiece whispers the secrets of the universe, waiting to be uncovered by those who dare to listen. The stellar masterpiece, an unassuming presence in the local group, holds a treasure trove of cosmic marvels that continue to defy expectations. Though the spiral artisan may seem less imposing than Andromeda or the Milky Way, its intricate structure and evolutionary narrative tell a story of resilience, dynamism, and cosmic grandeur. A galaxy of contrasts, serene yet active, ancient yet teeming with new life, it remains a profound subject of study. One of the most enchanting aspects of the celestial symphony is its relentless star formation. While many galaxies of comparable size experience a decline in stellar births over time, the cosmic luminary defies this trend. Its spiral arms are adorned with vast regions of glowing hydrogen gas, stellar nurseries where countless stars ignite. Among these, NGC 604 stands as a breathtaking example, harboring hundreds of massive, young stars whose intense ultraviolet radiation sculpts surrounding clouds into intricate cosmic landscapes. Visible even from Earth, this luminous nebula offers a glimpse into conditions that may have shaped the earliest galaxies. The ongoing star formation within the nebular enigma raises profound questions about its gas supply. How has the galactic wanderer sustained such prolific activity for billions of years? Observations suggest that streams of intergalactic gas continue to replenish its reserves, possibly remnants of ancient cosmic filaments connecting it to the larger structure of the universe. These discoveries provide crucial insight into how galaxies sustain themselves and offer a window into the conditions of the early cosmos. The gravitational mystery also stands out for its near-perfect balance between luminous matter and its vast dark matter halo. Its rotation curve, tracing how the speed of stars and gas changes with distance from the center, offers one of the clearest confirmations of dark matter. Unlike galaxies shaped by violent mergers, the cosmic sentinel's relatively undisturbed structure provides a pristine environment for studying this mysterious component of the universe. Yet, its dark matter distribution appears unusually smooth, challenging traditional models and fueling debates over alternative theories, including modifications to our understanding of gravity. Beyond its spiral arms and dark matter halo, the stellar nomad is an invaluable resource for understanding galactic evolution. From ancient globular clusters that orbit its core to brilliant blue giants scattered across its arms, its diverse stellar populations serve as a cosmic timeline stretching back billions of years. The Triangulum Wonder contains a remarkable variety of star clusters, each a microcosm of galactic processes. Some, formed in the galaxy's infancy, contain stars as old as the universe itself, while others are still actively forming new stellar generations. Perhaps one of the most surprising revelations about the Spiral Weaver is its gravitational bond with Andromeda. Though dwarfed by its larger neighbor, the intergalactic Voyager exerts a subtle but measurable influence on Andromeda's outer regions. Simulations suggest that the two have been engaged in a gravitational dance for billions of years, exchanging gas and stars during close encounters. These interactions likely helped shape the galactic sculptor's distinctive spiral structure and sustained its ongoing stellar production. The future of the celestial tapestry is equally captivating. Its eventual merger with Andromeda promises to be a cosmic spectacle of unparalleled scale. As the galaxies draw closer, tidal forces will stretch and distort their structures, forming luminous streams of stars and gas. This process, rather than a mere act of destruction, will be one of creation, blending their stars, planets, and dark matter into a new, massive elliptical system. This transformation will reflect the cyclical nature of the universe, where even in destruction, new cosmic structures are born. The spiral companion's interactions with its cosmic neighbors have left lasting imprints on its structure. Faint tidal streams of gas and stars linking it to Andromeda provide evidence of gravitational forces that have shaped the local group for eons. These barely perceptible trails, remnants of past encounters, hold invaluable clues about how material flows between galaxies. Some studies suggest that the cosmic tapestry may have lost portions of its outer structure during these encounters, potentially explaining the presence of an extended gas halo surrounding both galaxies. Dark matter, the invisible framework that shapes the cosmos, plays a crucial role in defining the celestial puzzle. Its rotation curve, remaining nearly flat even at great distances from the galactic center, confirms the existence of a massive halo of unseen matter enveloping the galaxy. Yet, its distribution does not conform entirely to predictions, hinting at complexities in the nature of dark matter that remain unresolved. The gravitational enigma thus remains a critical testing ground for both conventional dark matter theories and alternative models of cosmic structure. Ultimately, the galactic nomad remains a guiding light in our exploration of the universe. The James Webb Space Telescope will soon unveil even more hidden details, while next-generation observatories will map its gas dynamics, revealing the gravitational forces shaping its evolution. The discovery of exoplanets within its arms, though a distant dream today, could one day expand our understanding of planetary formation beyond the Milky Way.